Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the pure capacitive circuit. So you can see that this is a circuit which contains a pure capacitance and a alternating voltage source. Let us name this source as V is equal to V naught sine omega t. So this is a alternating voltage source and a current I is flowing in the circuit. Now we have to find out the current flowing in the circuit as a function of time, and obviously we cannot write it down like we did in Ohm's law. Like we wrote in pure resistive circuit I as V by R, but we cannot write it here because there is no resistance here. So we have to treat this circuit differently. So we can see that, let's suppose at any instant of time the charge appearing on this plate of the capacitor is plus q and on this plate is minus q. So we can write down q as cv and q will be cv. V will be v naught sine omega t. Okay, and the current flowing in the circuit will be I will be equal to dq by dt. So dq by dt will be cv naught into omega cos omega t. This is the current flowing in the circuit. So we can write down I as v naught upon 1 upon c omega or omega c. Okay, we can write down I as this. And this is sine, in fact, cos omega t. This is cos omega t. Now this term is xc. Xc. Now, if we compare these two terms, first of all, we can say that the complete term, this one, which is V naught upon 1 upon omega c, is dimensionally the current, because we know that cos omega t does not have any dimensions, and here the quantity which is present is current. So the dimensions of this quantity will be the current, and we can easily predict that the peak value of cos omega t is 1, and therefore this quantity will be the peak value of current. So this is I naught, which is the peak current, and this is V naught by XC. Let us name this quantity with a symbol. Let us assign a symbol XC. C is in subscript, and this XC has a name, and it is called as capacitive reactance. Okay. Now, if you compare it with the general form of Ohm's law, in which we say that I is equal to V by R, so this quantity must be having the dimensions of resistance. So I can easily say that the unit of this XC will be ohms, and its dimensions will be also equal to resistance dimensions. Now, what is Xc? Xc is also called as capacitive reactance, and it is the resistance offered by capacitance in uh, pure. In fact, the resistance offered by capacitance to alternating current. Okay, this is capacitive reactance, and we have already studied the RC circuit in the previous chapters. In the current electricity or capacitance, we have studied the RC circuit, and we studied that the capacitance offers infinite resistance to the DC current when it is 100% charged. So if we talk about this Xc in more detail, then we can say that Xc is 1 upon omega c, where omega is the angular frequency of the AC current which is flowing in the circuit. And for high frequency AC, for high frequency AC circuits, omega is very high, so XC is small, which means that for high frequency AC circuits, the impedance or the resistance offered by the capacitance is very small. Xc is very small. Okay, in high frequency AC circuits. This is the first thing. And for low frequency AC circuits, Xc is very high. So this capacitance offer a very high resistance to low frequency AC circuits. Now, if we talk about Xc for DC, direct current, so we can easily say that Xc for DC will be infinity because omega DC is infinity. In fact, zero, because DC current does not change its direction. Therefore, omega DC will be zero, and therefore we can say that Xc, the capacitive reactance for DC current, will be infinity. And this is already a proven result in the previous RC circuit, in which we have already studied that capacitance offers a infinite resistance to the DC current in its steady state. And obviously, we always consider the circuit to be in the steady state in DC. Okay, because the transient state is very small period of time. It stays for a very small period of time, so we can ignore that period and we can consider any DC circuit to be in steady state always. Okay, now if we talk about the current, so the current will be I naught as cos omega t. If you remember, the function was cos omega t and the voltage function was sin omega t. So it clearly indicates that we can first of all write down the cos omega t as sin pi by 2 minus omega t, or we can also write down it as I naught sin pi by 2 plus omega t. But obviously you can predict the correct one, because this is wrong, because in this case you have taken the sign of omega as negative, which is not that true, because originally omega is positive, so you cannot make the omega as negative. So the correct one is this one. So I will be written as I naught, where I naught was, we have already written I naught was the peak value of voltage V naught upon capacitive reactance. So I is equal to I naught, this is sine omega t plus pi by 2. It indicates that the current in, this is the main thing in the AC, that you have to remember all the phases, that what is the phase difference between the current and voltage in pure resistive circuit, in pure capacitive circuit, and in pure inductive circuit, which we will be studying in the next video. But in pure resistive circuit, we already have studied that the phase difference between current and voltage was 0 degree. And in pure capacitive circuit, we know that the phase difference between the current and voltage is pi by 2. So in pure capacitive circuit, we can say that current leads voltage by pi by 2 in phase. Current leads voltage by pi by 2 in phase in pure capacitive circuits. Okay, this is very important thing. And if we draw the phasor diagram, so we can easily say that while drawing the phasor diagram, we always draw it at t is equal to 0. So at t is equal to 0, the phase of voltage, which was the phase of voltage was omega t. So it was 0 at t is equal to 0. So we can draw the voltage on x-axis considering phase as angle, and we can draw the current on the y-axis considering uh, phase as angle, because the initial angle of initial phase of current is pi by 2. So we can say that current leads the voltage by pi by 2. And also if we draw the diagram of wave, current wave and voltage wave, so we can draw that voltage was a sine function and the current is a cos function. So there is a this is I naught and this is minus I naught. So there is a obvious phase difference between voltage and current. Okay, current leads by pi by 2. And obviously, if we talk about the average power loss, so it was denoted by the formula Vrms, Irms, cos phi. So phi here is 90 degree. So cos 90 is 0. So obviously average power loss in this circuit is 0. Because we always have studied previously that among L, C and R, only R, which is the resistance, is the element which loses the electrical energy in form of heat. Otherwise, capacitance and inductance always store the energy. So therefore, in a complete cycle, we can say that the average energy stored by the capacitance will be zero, or average power lost by the capacitance will be zero, because in this circuit there is no resistance present. Okay, and this is the important fact, and therefore we can say that the current flowing in the pure capacitive circuit is RMS current. In fact, is wattless current, because it does not contribute in any power loss. Therefore, we called such current as wattless current. And what you know is the unit of power. So wattless current is the current which does not contributes in any power loss in the circuit, and the power loss, average power loss in the capacitive circuit is zero, and therefore we can say that the current flowing the pure capacitive circuit is wattless current. Thank you guys. In the next video we'll be discussing the pure inductive circuit. Thank you.